Okay, so I think let us just quickly recap what we were doing last time, just so that we refresh our memories. So we were looking at basic concepts of extraction. We had seen all these concepts in our UG course. We were just trying to refresh. We looked at, first of all, what is distribution coefficient. Then we looked at how distribution coefficient is related to the activity coefficients and how they are related to interactions between the solvent and the solute and the water or aqueous phase and the solute that we are trying to extract. We looked at how octanol water partitioning coefficient tells us about the nature of hydrophobicity or hydrophilicity of the substance and why that is so important. And then we looked at we did some very quick calculations, very basic preliminary chemical engineering kind of calculations, where we did the amount of solvent required for single stage or multi-stage cross current or multi-stage counter current. And so we know that every time we need to do extraction, we should be trying to do multi-stage counter current extraction. That's the only way we can reduce our solvent requirement to the minimum minimum possible. Single stage extraction requires huge amount of solvent, and counter current multi-stage requires the least amount of solvent. So we should be trying to look at doing multi-stage counter current. And then what we tried to do was sort of recollect our rate based approach. So these kinds of diagrams where we draw the equilibrium line and where we draw the operating line and we draw the number of stages, this is an equilibrium based approach. And then we talked about the rate based approach, where we'll have to calculate the mass transfer coefficients of the continuous phase as well as the organic phase, and then we try to calculate the number of transfer units. So this is the rate, this is the approach that we are going to follow. And what we saw last time towards the end of the lecture was trying to look at different equipment. So we looked at mixer settlers, we looked at rotating disc contactors, we looked at spray column, packed column, pulsed extraction column, annular centrifugal extractor, and so on. And we tried to look at some of their basic characteristics. For example, let's say mixer settler, if you look at, you will have only one theoretical stage per pair of mixer and settler. So obviously if you need multiple stages and counter current, you will need many mixer settlers in series. That's going to occupy a lot of that's going to of course cost a lot, as well as that's going to occupy a lot of floor space. Whereas some of the other equipment which ensure a continuous contact, and they can give you multiple number of stages, and therefore you can have it as a column, and therefore the floor space would be low, and then the cost also would become low. So some of these qualitative advantages and qualitative what shall I say, qualitative characteristics of these different contactors, that's what we have seen. What we will do today now is to look at what are the important design parameters and how do you measure or estimate them. So if you look at the counter current extraction problem that we did last time, so we had a aqueous phase coming in, we had a aqueous phase going out. So let's say aqueous in and aqueous out. We had organic in and organic out, right? And to calculate the height required or the number of transfer units required, what did we do is we took a small element dz, and then we wrote a balance for the solute. Let's say A is our solute, or P, whatever that we took last time. So flow rate of, let's say, the aqueous phase multiplied by concentration change for the component A that is getting extracted in the aqueous phase. So in this particular case, if you look at Z is equal to 0 here, and Z is positive upwards, and therefore we don't have a negative sign here. And we said that this is equal to rate of extraction in this small element, rate of extraction in this small element. So rate is per unit volume, and then we multiply by the cross-sectional area. So A is our cross-sectional area and dz, and then this rate of extraction we wrote from the two film theory, if you like. So we had an aqueous phase, we had an organic phase, and the concentration profiles in the aqueous phase were like this. So we had Ca, oops, sorry, we had Ca at the interface in the aqueous side, correct, and then it dissolved or equilibrated in the organic side. So we had Ca at the interface on the organic side, and then there was some mass transfer resistance, and then we had this Ca in the organic side. Okay, and then we wrote this rate based on the mass transfer coefficient on the aqueous side and mass transfer coefficient on the organic side. So if you have any doubts, you can always refer to the previous lecture. Video is there. And so if I have to estimate the height required, and if I have to estimate the number of transfer unit required, I need to estimate this rate of extraction, and then this rate of extraction would depend on the mass transfer coefficient, the aqueous side mass transfer coefficient and interfacial area, as well as the organic side mass transfer coefficient and the interfacial area, right? So what we need to do is estimate the mass transfer coefficients. So that's going to be one of the design parameters. Next is this interfacial area. Now this is going to depend on how many drops are there. So if I have drops that are going up of the organic phase, the interfacial area, if I assume these drops to be spherical, this interfacial area is going to be decided by 6 times hold up of the dispersed phase divided by the drop size of each one. So if it's a spherical molecule, we just take it as d. If it's a distribution of molecules, we generally take this as a Sauter mean diameter. I hope you remember what is meant by a Sauter mean diameter. Sauter mean diameter is a, so it is denoted as D32. It's pronounced as 32, but it is actually D32. 3 being, it is suppose I have a bunch of drops, each one of different size, right? Then what this is summation of all the drops cubed divided by summation of all the drops squared, right? Diameter squared. So that means the numerator is like the volume and denominator is like the surface area of all these drops put together. So what this does is that it gives you a sort of an averaged out interfacial area per unit volume. That's how this di cube, it is a volume by area mean. So that's how this 3 refers to this cube here, and 2 refers to this power 2 here. So area and volume. So we need to not only know the hold up, we also need to know the drop size distribution so that we can calculate the Sauter mean diameter. Okay. The next thing is, we had assumed last time in the problem that it was all plug flow. So this plug flow assumption is what had allowed us to write a differential balance over this dz, right? If this differential element, if the flow of the phases aqueous and organic was not as a plug flow, then can you tell me what kind of correction would you have had to make? Right. So think about what we had talked about when we were talking about RTD. You might want to revise that as well. So if it was well mixed, then we would have all this concentration equal to the Ca out. If there was a dispersion coefficient in the aqueous phase, dispersion coefficient in the organic phase, then this is the convection term, isn't it? Convection. Along with convection term, we would have had to account for turbulent dispersion as well. So we would have to write dispersed plug flow model. recall that? If not, just go and quickly revise your CRE classes. So you would have had to suppose this A is taken on this side, left side, then this Q by A is nothing but velocity of the aqueous phase. So this is velocity of the aqueous phase into concentration at Z and dispersion coefficient. Do you remember that? Do you remember dispersion coefficient into the gradient at Z and then minus Z plus delta Z? And then on the right hand side we would have had to write the rate of extraction and dz, right? So this part we have neglected because we have right now said it is totally plug flow. Okay, so dispersion coefficients are required, and of course pressure drop is required because that's how it tells you how much power is required to pump this organic and aqueous phase throughout the column. That's going to tell you how much electricity you are going to consume. That's going to tell us what is the operating cost of your column. So what we will do now is look at all these different equipment that we have seen qualitatively last time, and we will try to do a little bit more quantitative analysis in terms of these parameters, So what we'll do is for spray column, we'll take spray column, and we will see how we can get all these quantities. Okay, then we'll take one more equipment, let's say maybe mixer settler or maybe rotating disc contactor, and then we will try to see how to get all these parameters, and then we'll finally do a design of each of these things. So get your calculators out. We will be doing some kind of calculations. Okay, there's one more thing that I wanted to talk about is let me just rub all these arrows. Erase all ink. Right. So how would you estimate this hold up? Hold up can be estimated by very simply taking photographs, or drop size distribution you can estimate using photographs. Mass transfer coefficient you can estimate using actual extraction experiment, right? Maybe some of these experiments you would be doing once you come to institute for the Cheminge lab. Dispersion coefficients can come from RTD experiment. Pressure drop of course can come from some instrument. Okay, so not very important just now, just to tell you that there are different ways of measuring these kinds of things. Right now what we'll try to do is first of all look at the design principles. That means try to look at all these parameters for, let's say, dispersions that are created by density difference. Now do you remember what kind of equipment we were talking about? When I am supplying energy only by way of density difference or pressure difference between the phases, that means if I have an organic phase, I sparge that organic phase at the bottom. Droplets of this organic phase are going to go to the top, so that's like a spray column. And if you want to think in terms of a gas liquid equivalent, that would be a bubble column. Now, so what we'll try to do is try to look at these principles now based on for, let's say, spray column. Okay, so first of all, don't worry about all these equations. You don't have to mug up any of these equations. And what we will try to do is to look at what is the basis behind these equipment. And once I know basis behind these expressions, then I can always use and I can always apply them. Okay, just give me a second. I'll just have a glass of water. Okay, so here's the first concept. So think about this. Think about a spray column. So spray column, you are going to have drops of the dispersed phase going up if it is light phase that is dispersed, or drops of the heavy phase going down if the heavy phase is dispersed. What we are going to have is, if you imagine this as a spray column, so imagine this as a spray column, we have drops going up in this particular case, let's say. So this light phase is dispersed by way of a distributor, and the drops of the light phase are formed, and then they are going up. The heavy phase is coming down. So if you think about this equipment, the light phase here is the dispersed phase. Dispersed meaning whichever one is flowing in the form of drops, and the heavy phase is continuous. Continuous in the sense that it forms a continuum in which the dispersed phase is flowing upwards. Okay, so we are going to call D, or we are going to denote D as a dispersed phase, C as a continuous phase. We are going to write U as a superficial velocity. So UC is a superficial velocity of the continuous phase. UD is a superficial velocity of the dispersed phase. I hope everybody knows what I mean by superficial. Superficial means flow rate divided by the total empty cross-sectional area. Right. Now, epsilon D is the holdup of the continuous phase. Holdup of the dispersed phase. Epsilon D is holdup of the dispersed phase. That is what is going to give you the interfacial area. Okay. Now, if the phases are going counter current to each other, that's what we want when we are doing extraction. We want counter current flow of the phases. So UD divided by epsilon D would be the actual velocity of the dispersed phase. UC divided by epsilon C, or UC divided by 1 minus epsilon C, would be the actual velocity of continuous phase. Actual velocity of dispersed phase. Now, because they are flowing counter current to each other, the resultant velocity would just be the addition of the two. So this is your resultant velocity. If you are not able to visualize this resultant, let me give you an example. Let me give you a small example. Imagine that you are trying to catch a train. Okay, the train has started going in this direction at 1 meter per second. If you are running at this in this same direction at 0.5 meters per second, the relative velocity would be 1 minus 0.5. Right? Train would be going at 0.5 meters per second faster than you. Okay. If there is another train going in the other direction, let's say at 3 meters per second, the relative velocity between the two trains would be 3 plus 1, 4 meters per second. Right? So it is the same way. It is just basic classical mechanics or classical Newtonian mechanics. This relative velocity or resultant velocity, or let's call it better, would be relative, because it is velocity relative to each other. It is a relative velocity between the phases. Velocity of one phase relative to the other phase. Right? This must be equal to the what is called as a slip velocity. Slip velocity. So if I take a single particle, in an infinite medium, single droplet if you want, in an infinite medium, then this epsilon d is tending to 0, and then there is actually no continuous phase velocity, infinite medium, so UC is equal to 0. Imagine one drop rising in an infinite medium, so UC is equal to 0. Now the velocity would be, the relative velocity would be equal to the terminal settling velocity of the droplet. Right? So this is like a terminal settling velocity of a droplet. and this 1 minus d, 1 minus epsilon d raised to m, this takes care of the hindrance effect. Do you remember when we were talking about fluidization, you would have done something called as hindrance effect, you would have done something called as a Richardson-Zaki index. Do you remember that? Anybody? Richardson-Zaki index or Richardson-Zaki correlation, where you relate the minimum velocity for fluidization with the terminal velocity of those particles. You had terms like this, Vmf by Vt equal to something something epsilon raised to some number. You must have mucked up all these things, or you must have seen them sometime earlier. So, but it takes into account the effect of hindrance because of the presence of multiple drops. It is not just one drop that is rising, it is a bunch of drops or a collection of drops that are rising. So this expression allows us to relate the velocities and the hold up by what we call as the using the slip velocity. Sometimes it is also called as a drift flux kind of a model. It is telling you the flux of the continuous phase and flux of the dispersed phase relative to each other. So what people did is people did experiments. People measured the UD, people measured the UC, people measured the epsilon D and back calculated the value of U0, which is like a characteristic droplet velocity. Now remember, this is a characteristic velocity. It is not like a terminal velocity because the droplets are not uniform, the droplets are not spherical, so it's not really a good idea to we can't really estimate it very quickly. So it is called as a characteristic droplet velocity rather than a terminal velocity. So people did experiments on spray columns with different kinds of densities, different kinds of viscosities and so on, and correlated this U0 by this empirical equation. So these kinds of equations are there. These are coming from experimental data. They are empirical in nature. Empirical in the sense they are fitted, the correlation is fitted to match the experimental data. It is fitted to match the experimental data. Okay, what we will try to do is we'll do some calculations, but let me go little forward, and then after that we will calculate all these things for some set of physical properties. This UN is nozzle velocity. This distributor that is there, we can take a look at this one distributor and how much of the dispersed phase goes through this one distributor, what is the velocity through that one distributor. That's our value of UN. Now what I want you to do is, all this we are doing qualitatively, just trying to understand what happens. I want you to plot epsilon D versus either UD or UC. How would that graph look like? Can you draw for yourselves in a couple of minutes? Let's try to analyze what will happen. If I think about it, the phases are going counter current. So if I increase UD, okay, I'm having more and more of the dispersed phase going in the column, right? So hold up is going to go up, epsilon D is going to go up. But remember, this epsilon D, the drops that are rising, they are coming across or in opposition to the downward flow of the continuous phase. So if the number of drops rising becomes so large, then the velocity through which or the area through which the continuous phase has to come down keeps on reducing, and therefore now the drops going upwards face stronger and stronger resistance due to the presence of the continuous phase which is coming down in this particular case. So I have drops that are going up, but the continuous phase is continuously trying to sort of bring these drops down. So these drops will come closer and closer to each other. They will coalesce and if they will coalesce, they will become one big huge drop rather than so many drops. And then it is as if this whole column will be filled with this dispersed phase. We would call that as flooding. Just like we had seen flooding in a gas liquid packed column, where the upward flow of gas and a downward flow of liquid. At flooding, you have liquid which is trying to come down is no longer able to come down. The gas is trying to force its way, and it floods the whole column with liquid. So in this same way, this liquid extraction column also floods up. So how do you mathematically characterize this flooding? Well, if I have to mathematically characterize, I would say d epsilon d by dud should become infinity, isn't it? So if it was y versus x, we would have said it is reaching infinity, slope is becoming infinite. That means dy by dx is becoming infinity, right? But that's not very convenient way to evaluate. What we would rather evaluate is dud by d epsilon d to become 0. Same way, if you think about, we keep the ud same now, we increase uc now, again something similar will happen. Beyond a certain value of uc, maybe at a different value of uc, the column will flood, because the continuous phase, so much of continuous phase is coming down that it prevents droplets from going up, and therefore they become the holdup keeps on increasing. So the same way we could characterize flooding as duc by d epsilon d equal to 0. Now we already have one relationship between between the ud and the uc and the epsilon d. What I want you to do is rewrite this expression with ud on the left side and everything else on the right hand side. What that right hand side would be now? That right hand side would be some function of, let's say, f1 u0 epsilon d and uc, and of course m, but m I'm saying is equal to 1 just now. Okay, I'm just rewriting this expression. Same way, I will rewrite this expression in a second way, is uc equal to some function of u0 epsilon d and ud. Okay, now I want you to differentiate this expression with respect to epsilon d and equate to 0. So dud by d epsilon d equal to 0. Differentiate and equate it to 0. I will get some expression, I will get some relationship between u0 epsilon d. Now that epsilon d, we will call it as epsilon d at flooding, and uc. Okay, this expression I want you to differentiate with respect to epsilon d, equate it to 0, and we will get an expression between u0 epsilon d, which is now at flooding, and ud. Okay, this would be equal to, something would be equal to 0. Now eliminate u0 between these two expressions, and you will get a relationship for holdup at flooding. Okay, don't trust me, you can derive it for yourselves. Okay, I'm just reducing the time, you can do it for yourselves. What we will try to do is we will use all these expressions for some example. So let's say continuous phase is our aqueous phase, dispersed phase is our organic phase. So these are the densities, viscosities, interfacial tension. Diffusivities are there. We will need diffusivities for calculating mass transfer coefficient and so on. UN, suppose UN is 0.25 meters per second. Okay, I want you to calculate U0 using this expression. I want you to calculate U0 using this expression. Okay, once you calculate U0, Suppose UD by UC ratio is 0.5. I want you to calculate epsilon D at flooding using this expression. So let me just say calculate U0. Let me say here using equation 1, using equation 2. So this is our equation 1, this is our equation 2. And then suppose I say that in the actual column we want 70% of the flooding hold up, or 60% of the flooding hold up. We can't have 90% of the flooding hold up because then the margin would be very small. If the flow rates change a little bit, our column will flood. So we keep some kind of safe margin, let's say 60 or 70% of the flooding hold up we want in the column. Then I want you to calculate what should be the value of UC and UD using equation 3. Okay, this is our equation 3. Okay, would you be able to calculate now? I'll give you 5 minutes to calculate. Just to make sure that everybody has understood and everybody is able to do, let's quickly do all these calculations very quickly. We will see the solution. You already have the answers. So this is like a Froude number. It tells you what is the importance of gravitational force on the drops. That's going to tell you how fast that drops are going to rise upwards in terms of their because of the force, gravitational force on them. This is not a dimensionless number. This raised to 0.25 will have dimensions of meters per second. So if I take SI units here, I better take SI units here, and then all these things would have the units of this number raised to 0.25 would have units of meters per second. Just to make sure that everybody is understanding, sigma surface tension has units of Newton per meter, delta rho has units of kg per meter cube, g is meter per second square, rho c square is kg per meter cube square, kg square meter raised to 6. Now 1 kg per meter cube I can cancel out. Okay, and this Newton I can write it as kilogram meter per second square. So this will become 1, so kgs can go away, right? 1 meter can go away. I will be left with meter square here, which comes in the numerator. So this will become meter raised to 4 second raised to 4 raised to 0.25 raised to 1 by 4. Then this U0 will have units of meters per second. Okay, let's just put these numbers. 1.088 sigma 0.03, that's what we had. Sigma, that was what we had, 0.03. Just see that it is there, 0.03, yes, 0.03. Delta rho 1000 and 900, so this was 100, 9.81. Rho c, rho of the continuous phase is now aqueous phase, 1000 square raised to 0.25, un square 0.25, okay, to 9.81, nozzle diameter 0.003. This raised to very small exponent. These exponents and this constant are coming from experimental data. These are fitted to match experimental data. Somebody has done experiments in the past and somebody has fitted these constants to their experimental data. Okay, so that's how we can calculate this U0. Once I tell you the UD by UC is say 0.5, then it's very straightforward. Epsilon df can be calculated, and once you calculate epsilon df, we can take epsilon d to be 70% of epsilon df. Now here we will know epsilon d, we will know m, we will know u0, m is of course 1. This is known, this is known. The only unknown is this ud and uc. Either we can substitute for ud into uc or uc into ud, in whichever way you want, because the ratio we know, ud by uc is equal to 0.5, and then we can calculate the uc required or the ud required. We will see all these calculations when we start coming to one full equipment design. But let's go forward now. What did we want? We wanted to get the hold up, right? Drop size distribution is something that we will talk about now. Okay, then we'll talk about mass transfer coefficients. Okay, so whenever you are creating a dispersion, you are always going to have a size distribution. You are not going to have all the drops having the same size. The drops will have a size distribution. So Gaussian distribution, random distribution is one such kind of distribution. But most often experimentally, what is found is that the size distribution is not Gaussian. It is not like a random phenomena. It is more like a log normal kind of a distribution, and this is how log normal distribution looks like. So PDF is nothing but the number density if you want, and X is like the size of the drop. So this is how the number distribution of the drops look like. If it's like the red curve or the green curve or the blue curve, depending on how widely spread that distribution is. If the drop has a very narrow spread, then it will be like this red one. If the drop sizes have a very wide distribution like this blue one, then that spread would be large. So this sigma parameter tells you the spread variance, if you like, standard deviation. We have been using that when we were talking about RTD as well. And mu is the mean drop size. Okay, so mu and sigma are the two parameters that are required to characterize this log normal distribution. Let's not worry about this just now. We have already said that we are going to calculate not using the size distribution. What we will do is we will discretize this size distribution. Let's say it's a red is the actual measured value of drop size distribution. We will discretize that, and then for each bin or each interval we will calculate our D32 sorter mean diameter is summation over all such intervals, number of drops in that interval, diameter of that interval to the power 3 divided by number in that interval and diameter in that interval square. Okay, so that's how. So this is like the cumulative volume of all the drops put together, cumulative surface area of all the drops put together. So it's called as D32. Okay, so what I want you to sort of visualize now is I'm not going to give you a size distribution, but what we are going to talk about is how do I estimate this sorter mean diameter for spray columns, right? Okay, so when you think about process of formation of drops, so if you imagine this is your nozzle, just give me a second, 1 second. So if you imagine nozzle, so this is your nozzle, dn is your nozzle diameter. Now you imagine that this dispersed phase is coming from the bottom through this nozzle, and it is going to form these drops that are generated inside the spray column. So if you imagine, the drops would become like this with time. If I visualize, the drop would become bigger, the drop would become bigger, the drop would become bigger. Okay, and when the buoyant force on the drop becomes large enough, then this drop will detach and I will have a drop which is going into the spray column. And then once this drop goes away, now a next drop will start forming, and it will grow and it will grow, it will grow till the time that buoyant force becomes large enough to overcome the surface tension forces. Then the drop will detach from this orifice, nozzle if you like, or a sieve plate if you like, and then the new drop will go into the spray column. So what dictates the size of the drops that are formed is a balance between the gravitational force. Now when I say gravitational, it is actually gravitational minus buoyant force. Net gravitational, buoyancy and gravity, both these. So net gravity minus buoyancy, that's the kind of force. So although I'm writing it as gravitational force, it is actually gravitational minus buoyancy, or net gravitation if you want. And the surface tension force. So if you think that there is a drop of size d, okay, then the gravitational force on that drop would be pi by 6 d cube delta rho. So it is a net gravitational, gravity minus buoyancy multiplied by g. This would be the uh, gravitational force, and the surface tension force would be surface area pi d square and the surface tension force. Is that right? Oh, it is pi d into sigma. That's the force. The perimeter, if you like, pi into d is like the perimeter of sort of related to the, it could be dn or it could be d if you like, the perimeter across which that surface tension force is acting, right? So this balance between the two forces is governed by a dimensionless number, like we have seen Reynolds number or other such dimensionless numbers we have seen. It is called as an Eötvös number, or sometimes people also call it as bond number, BO. So if you take this ratio, forget about that 6 just now, okay, if you take this ratio, d has cancelled out, d square delta rho g by sigma. So this tells you relative importance of the surface tension force on the drop as compared to the net gravitational force on the drop. And the drop detaches when this is almost of the order 1. Forget that 6 part is there. Actually that 6 part is here. Okay. So one of the ways in which what people do is you can recommend a size of a nozzle so that this gravitational force and surface tension force is around 1 if you like, right? It's not 1, I mean it's not 1, but it is the ratios in terms of, you if you want to think in terms of an equivalent bond number, is of the order 1. So that's how the typically size of the nozzles are decided, and depending on that size of the nozzle you can calculate the Sauter mean diameter based on uh, this kind of a relationship. So again, people have done experiments. People have actually measured the Sauter mean. People have actually measured the drop size distribution using some kind of a method, let's say photographs or whatever, and then calculated the D32. Did these experiments over a large range of sigma and delta rho and g and un and dn, and correlated this empirically. Okay, so again, this is an empirical correlation. Okay, I want you to calculate dn, whether this dn that we took as 3 millimeters, 0.003 meters, is it falling in this range? Okay, and I want you to calculate D32 based on this physical properties. Okay, and once you calculate D32, you can calculate the interfacial area as 6 multiplied by hold up divided by D32. Okay, just a couple of minutes you can take and calculate all these things. Okay, let's go forward. Next thing that we would like to estimate all these are fairly straightforward. You can just substitute the values and calculate. The next thing that we would like to calculate now, what is the next thing? What is the next design parameter? Next design parameter is our mass transfer coefficients, right? Right. We have seen hold up, we have seen drop size distribution, we have seen mean drop size. Now the mass transfer coefficients. So again, people have done experiments and made some empirical correlations for for mass transfer coefficients. So I'm just going to give you two such empirical correlations. There are several that people have proposed. So this is like your Reynolds number, droplet based Reynolds number, okay, and this is like your Schmidt number. Okay, normally you would want a Sherwood number here. So this is like a Sherwood number, but it is not the usual kind of Sherwood number. Some more things are there in this. This is like your uh, Stanton number, if anybody remembers. But okay, it's like a Sherwood number if you want. It is Sherwood number divided by RE and Schmidt. Uh, so such empirical correlations are there. People have done experiments, measured the values of these parameters and correlated them empirically. So these constants that are there, they are coming from empirical, they are coming from experiments, and they are fitted to match the experimental data. So the continuous phase mass transfer coefficient Kc and the dispersed phase mass transfer coefficient Kd. And US is our slip velocity. Remember what US is. US is U0 multiplied by 1 minus epsilon d raised to the power m. M is usually 1. So US is equal to U0 into 1 minus epsilon d, right? So take all these values now, whatever you have calculated so far for U0, epsilon d, D32, all the physical properties, okay, and calculate the values of Kc and Kd. And once you calculate Kc and Kd, interfacial area already we know. We can calculate Kca and we can calculate Kda. Kca would be per second, Kda would be per second. Kc would be in terms of meters per second. Kd would be so many meters per second, and interfacial area is meter square per meter cube, right? So take the values that you have calculated so far and calculate these parameters, mass transfer coefficients. Okay, in case you are thinking about this is your Sherwood number divided by RE and Schmidt number. This is some constant 0.725, in this case Reynolds number raised to minus 0.43 and Schmidt number raised to minus 0.58. So if you just multiply throughout by Reynolds number and Schmidt number, then the Sherwood number would be minus 0.43 plus 1. This would become 0.57, and then this would become 0.42. So then the dependence of Sherwood number on Reynolds number and Schmidt number is proper, like 0.5, 0.6 and 0.5. That's what we have been talking when we did mass transfer and then when we did CRE, right? So don't think that this is something different. These exponents are coming just because we have divided by Reynolds number and Schmidt number. Okay, now what we will try to do is to use up all these correlations into a design. So this is the same problem that we took last time. Let's say product P is present in an aqueous stream. It is desired to extract 99% of P from the aqueous stream using an organic solvent. Inlet concentration of P in the aqueous phase is 5000 milligrams per liter. Flow rate of the aqueous stream is 10 meter cube per hour. Distribution coefficient of P in the organic solvent is 5, same as last time. Phase ratio, volumetric flow rate of organic solvent to that of the aqueous solution is 1.2 times the minimum. We saw last time how to calculate the minimum solvent ratio. Extraction is done in a counter current spray column. You can assume plug flow behavior of both the phases. Neglect mutual solubility of the water and solvent. Solutions are dilute so that volumetric flow rates don't change. And assume that the entering organic phase does not contain any P. Now I want you to find the diameter and height of the spray extraction column. We solved some similar problem, but that time I had given you the mass transfer coefficients and just to explain to you the concept of number of transfer unit and height of transfer unit. Now all the things we have to calculate and finally come out with what diameter I should have of the spray column and what height I should have of the spray column. Okay, I want you to try these calculations now. So what we'll try to do now is to just look at the sort of design procedure. We have done these calculations with these physical properties. So we'll just try to see what kind of procedure we adopt, and then we will we'll get the values just by actually doing it. So first thing that you would want to do is to sort of visualize the problem, right? So imagine this is your spray column. Your aqueous phase comes in. This is 5000 milligrams per liter of P. I want to extract 99% of it. So P going out is 50 milligrams per liter, 50 ppm if you like. Organic phase coming in, P is 0, and organic phase going out. Now first thing that we need to decide in a spray column is which phase are we going to disperse in what. So are we going to have organic phase through the nozzle and then drops of organic phase are going to rise upwards, or are we going to have the aqueous phase being dispersed and drops of the aqueous phase falling downwards? Okay, let's do like what we have been doing today. Let's assume that our organic phase is dispersed. So there is a nozzle, 3 mm, dn is equal to 3 mm, and vn, whatever vn we had taken, what value we had taken, um, un, 0.25 meters per second. 0.25 meters per second. Okay, so these drops of organic phase are going to rise upwards. Okay, so first thing that we want to decide is which phase is dispersed. Okay, right now let's just make some choice, but we can always do the whole set of calculations with the second aqueous dispersed, and we can see for ourselves which one requires bigger column, which one requires smaller column, and then accordingly we can decide right now. Right now we just assume something. Okay, so in this case assume organic. All right, next thing is we had calculated the minimum solvent ratio last time, right? This aqueous phase we are told it is 10 meter cube per hour. Aqueous phase is 10 meter cube per hour. Minimum solvent ratio we had calculated, and now we are going to take 1.2 times the minimum solvent ratio. Okay, everybody comfortable up to this point? If you're not comfortable, just go back to the recorded lecture, visit that lecture, and see for yourself that you are able to calculate the the solvent ratio, the flow rate of the organic phase. So Q organic we would know at this point of time. Okay, so that means what are we going to know? This we have assumed that aqueous is continuous phase, organic is dispersed. Okay, now based on the physical properties, now we should be able to calculate U0. That's what we did some time back, right? Then we would be able to calculate epsilon df. Now, if epsilon d is 0.7 times epsilon df, then we have also calculated the epsilon d. Hold up of the dispersed phase, hold up of the organic phase that we want. We had all done these calculations, right? And then once you know the epsilon d that you want, once you know the u0 that you have got based on the physical properties, based on the nozzle velocity and so on, you can calculate ratio also, you know, ud by uc ratio also, you know. So ud by uc is now the same as q of organic divided by q of aqueous. Dispersed phase is our organic phase, continuous phase is our aqueous phase. So the superficial velocities, ratios of the superficial velocity is the same as ratios of their flow rates. Why? Because superficial velocities are nothing but the flow rate divided by cross-sectional area. If T is the column or tank diameter and h is our height, that's what we need to find out, h and t, right? So divide by pi by 4 t square. So pi by 4 t square cancels from both sides, the numerator as well as denominator. So the ud by uc ratio is the same as the organic by aqueous flow ratio, right? And then you would be able to calculate the value of ud and you will be able to calculate the value of uc. What you had calculated were values slightly different, because that time we had assumed ud by uc to be 0.5. Now it may not be 0.5, it may be something else, because now it depends on the minimum solvent ratio and how many times this minimum solvent ratio that we are taking. Okay, so the actual ud by uc ratio will depend on now this minimum as well as the how many times the minimum that I'm going to take. So once you get the ud and uc and you know the flow rate, so flow rate you know, required ud you know, required uc you know, then you can find the diameter of the column. Are you with me? Now to find the height is straightforward. We had done that last time. Okay, all the properties I know, all the velocities I know, so we can calculate this d32. Hold up, we know d32 we can calculate. Once you calculate d32, you can calculate interfacial area, 6 times hold up divided by d32. Next, the mass transfer coefficients we know, kc and kd. Oops, sorry, this kc and kd, we have seen this. So kc and kd can be calculated. So kca and kda can be calculated. Now we can take a differential balance. Dz, and with this differential balance we had solved the problem last time. Last time I had given you the values of kca and kda, but now that we can actually estimate the values of kca and kda, can we not calculate the height required? Now mind you that the diameter of the column that we have calculated, let me highlight that, diameter of the column that we have calculated and the height that we have calculated, right, are subject to this assumption. We have assumed that the organic phase is dispersed. we have assumed that we want 1.2 times the minimum solvent ratio. Okay, of course it is also dependent on the validity of these correlations. We have used all these correlations, and it is subject to the applicability of these correlations to our our system. But okay, let's assume that, because somebody has done experiments over a wide range of parameters, and hopefully our value, our data would be in the range in which they have done experiments, so the correlations would be applicable. But the two main assumptions that we have made is, we have assumed that the organic phase is dispersed, and we have assumed that 1.2 times the minimum amount of solvent ratio is required. Based on these two, we have calculated the diameter and the height of the column. Now, this is just a simple set of calculations. These are some simple algebraic equations, simple equations which we can all solve, which we can all find find values. What I want you to do is change this 1.2 times the minimum amount, right? So I have taken 1.2. We can calculate the diameter of the column, and we can calculate height of column. Okay, but if I put this in an Excel spreadsheet, put all these calculations as formulae in the Excel sheet, I should be able to change just the value of this ratio 1.2, and then I would be able to get all the data or all the calculations done automatically. And then I can always just change the value of that cell and get all the values in just simple one shot. So I want you to try it out for different values of the minimum solvent ratio. So if I want 1.1 times the minimum, if I want 1.2 times the minimum, if I want 1.5 times the minimum, I should be able to calculate diameter and height, put it in Excel. Now you can change the phases also. We have taken organic to be dispersed, but so this set of calculations is, let's say, for organic dispersed and aqueous continuous. But you can operate the spray column the other way around also. I can have aqueous dispersed and organic continuous. What will change is, now the properties will change, right? Now the dispersed phase will be aqueous and continuous phase would be organic, isn't it? Okay, so if you do that, again you can use the same Excel sheet and calculate this table for different minimum ratio, minimum times the minimum, times the minimum, right? Then I want you to compare that out of these two tables, which one requires lower diameter, which one requires lower height. In general, which one would require lesser volume of the extraction column. Okay, and of course, yes, not to miss out, we have made one more very big assumption, is that we have made the assumption that plug flow behavior of both the phases. Okay, that is also a very big assumption. But generally, if the column is very large, because the Peclet number, if you remember your definition of the Peclet number, Peclet numbers, let me just write that. Peclet number would be UL by dispersion coefficient. Continuous phase would be UC, L length of the column, or in this particular case length we are calling it as H, UC, H and TC. So if this H is very small, then sorry, I mean if H is very large, then this Peclet number is going to become very large. Okay, but remember that UC is small. It is of the order of millimeters per second, 1, 5, 10 millimeters per second. So it's not uncommon to have Peclet numbers in the range of 20, 30, 50, rather than having Peclet number in the range of hundreds. So axial dispersion, yes, we do have to account for. Right now we have done it only for the case where axial dispersion is insignificant. Peclet numbers are very large. Okay.